Today we're going to be talking about two types of functions, exponential and logarithm functions. So, an exponential function is when there's an x as your exponent, and f of x equals a to the x is an exponential function with the base being a. The domain of this is all real numbers because I can plug in any x I want, but my y outputs are never going to be negative. So that's going to get me my range of y is greater than 0. Making the x asymptote, or y equals 0, your asymptote. And we have a growth function or a decay function, and that all depends on a few things. First, I want to talk about a few key points that we're going to first be graphing. Okay, so one of the key points is if you make your exponent negative, you get 1 over a. Make your exponent 0, anything to the 0 power is 1. And then 1 and a. And that's going to get you an idea of what the graph looks like when we start translating. Now, a growth function is as x gets really, really big, your y's also get really, really big. And a decay function is as your x's get really big, your y's get infinitely smaller. And both approaching that x-axis, which is your asymptote. Okay, graph that function, state the domain, range, and asymptote. And I'm going to write myself a little note here. Domain, range, and asymptote, so I remember to do that. Now let's talk about our translations. -3 means I move everything down 3. So this x-axis that was my asymptote, I move down 3 units. And I draw that in right away so that I know that that's like a floor I can never cross. And then +4 means I move everything left 4 units. So what I need to remember when I'm graphing is that I'm graphing translations of the 2 to the x function. So if I'm graphing translations of that, I find those key points that I talked about, and I translate these points is what I typically do. Anything to the 0 power is 1, get with it, and then 2. Okay, so what I do is I plot the point -1, +1/2. I translate this down 3 units, 1, 2, 3, and over 4. And I do the same thing. I have 1, 0, down 3, over 4. And then we have 1, 2, so, 1, 2, down 3, over 4. Remember, it's not a line, it has some curve to it. So our domain is all real numbers. The range, y is greater than whatever your asymptote was, which was -3, and your asymptote is -3. And this should be a review from both Algebra 2 and Pre-Calculus. That's why I went through that fairly quickly. Okay, one-to-one functions. This is important. When a function has one input, so each output is associated with exactly one input. So you have a couple different ways that we test. Well, one way that we test that is the horizontal line test. This function y equals x cubed is 1-to-1 because it passes the horizontal line test. Your graph only intersects at one point. Versus y equals x squared, that does not pass our horizontal line test. And what this means is going to be on our next slide. So inverses. So since each output of a 1-to-1 function comes from just one input of a 1-to-1 function, you can reverse them and find an inverse function. So if a function's 1-to-1, the inverse is a function. I can find the inverse of anything, but then the ability to be able to solve for y and to write it as an inverse, this is the notation we use for inverses, tells me that it is a 1-to-1 function. Now, composing a function with its inverse and you get back the value of x, that tells me that we have an inverse. Okay, so let's do an example. Remember, this means inverse. So I switch my x and my y to be able to find an inverse. And then I solve this for y. So I cross multiply. I get every term that has a y on it on one side, and get everything else that doesn't have a y in it on the other side. I factor out my y, and then I divide. And so then this is my inverse. Now finding the inverse for this function. So I switch my x and my y. Now remember how we solve for exponents, our logarithm. Log base 2 of x is equal to y plus 7. Subtract the 7 over. And we have now our inverse. So a new function is born. Hey, these two functions are inverses. That's why the domain of a log function is the range of its inverse. And the range of a log function is the domain of the inverse. And then remember that we have a few special functions. Log base 10 is called the common logarithm, and log base e is the natural logarithm. We use this log base e a lot in calculus. Okay, so base a and base e, these two things are the same thing. And what students don't realize, or what I think pre-calculus teachers might do a bad job of explaining, is why are these properties true? Well, if I make f of x the function a to the x, and I make g of x the function log base a of x, when I take my composition of f of g of x, which is this quantity right here, you simplify and you get x because those two functions are inverses. Okay, so graphing a logarithm. So graphing a logarithm is the inverse of graphing an exponential. So how I often look at this is to get my key points for a logarithm graph. Is I take away all my translations and I get the basic graph. Now I look at powers of 3. So 1/3 is 3 to the negative 1. 1 is 3 to the 0 power. 3 is 3 to the first power. 9 is 3 squared. So if I'm looking at powers of those, then you are set up in a good spot. Okay, so these are the points we're going to translate. The only difference here now is we have a stretch in the y direction because it's outside the function. So I'm going to take it, I'm going to multiply all of these y values by 2. And multiplying all those by 2, I'm going to graph each one of these points, and then I'm going to translate them left 3 and up 4. Before, your x-axis was your asymptote for an exponential. Now the y-axis is your asymptote, and you get your asymptote by shifting 3 units. So I shift everything over 3 units. I look at that kind of like a wall that we can't cross over. Okay, so normally I'm at 1/3 -2, and I'm going to shift this over 3 and up 4. I'm at 1, 0. I'm going to shift this over 3, up 4. Normally I'm at 3, 2. I shift this over 3 and then up 2. I'm sorry, up 4. I'm at 9, 4. I shift this over 3, up 4. I should only be up there. No, that first point I put down was right. Yeah, that one's right. Okay. So, now you have your graph. And you need to know what these basic shapes look like. Just a quick review of our properties of logarithms. You're going to need these when we start talking about some stuff later on in calculus. Okay, solving this guy for x. We add 9 over. Now you use logarithms to solve. Log base 2 of 17 is equal to x plus 5, and then I subtract 5 over. Using the change of base formula, this approximates to negative 0.913. Lastly, solving this for x. I need to break this 4x out. So e to the 3y plus 8 is equal to 4x. So I write it now as an exponential, because remember, logs and exponentials undo each other. Divide everything by 4. That's what we get when we're solving for x. Again, there is a Google form right below the video. Please make sure that is submitted on time.